The screen in the VGA mode I chose will have 640 times 480 pixels. That's a 4:3 aspect ratio, which is the aspect ratio of our beloved 8-bit retro computers. I've also chosen a pixel clock. There are few you can choose. I chose one of 25.175 megahertz for a very pragmatic reason. You can buy an oscillator exactly at this clock speed, so you don't even need to build your oscillator with the crystal capacitors and all that. This simplifies the whole thing. Now, for a VGA circuit, you have to generate not only the video information here on the screen or the frame, you also have to generate synchronization information. As you are drawing a line, putting all the pixels one after the other and sending it to the monitor, when you reach the end of a pixel line, you can't immediately go back to the next pixel line. That's not how it works. Before you go back, you have to wait a certain period of time. This is usually called the front porch. After the front porch, you have to send a negative pulse, which is called the horizontal sync pulse. It's active low. And after that pulse is sent, so the TV knows that, okay, he just finished a line, he's not waiting for nothing. After that, you have to wait a little bit again, and that's the so-called back porch. And the reason for this in the standard is that, in the old CRTs, once the electron gun reached one side of the screen, it couldn't instantly go back to the beginning again. It took some time until the deflectors would bring it back so it could scan the next line, and that time was given by the front porch, the horizontal sync pulse, and the back porch. To this day, it's still built into the standard, even though we have LCD screens now. But if I am to generate VGA video circuitry, I need this. And not only that, I need the same thing, or roughly a similar thing, for the vertical part. That's called the vertical sync pulse, and it also has a front porch and a back porch. So you need all that. So to do this, you need to count, according to the pixel clock. You need to count how many pixel clock cycles you've had, for instance, writing the first pixel line. By definition, that will be 640 pixel clocks, by definition. But then you have to wait 16 other pixel clocks for the front porch. Then you have to issue the horizontal sync pulse, which will take a certain number of cycles, 96. And then you have to wait a few more cycles for the back porch, and only then you can start writing the next line. So your VGA circuitry has to be able to count to these values here. And not only that, it needs to be able to detect when the counter has reached these values, because then it has to change what it's doing upon reaching these counter values here. And of course, the same thing applies to the other end, except that in this case, you're not counting according to pixel clock cycles, but you're counting according to pixel lines. How many lines have you written already, or the equivalent time to write a line? You have to count up to 480, because that's the last line of the frame or the screen. But then you have to wait a little bit more, the equivalent of another 10 lines, for the front porch, and then the vertical sync pulse, and then you have to wait a bit more for the back porch, and only then can you start writing out the next frame, the next screen that will be displayed. So the architecture needs to be able to do all this. So I would use a chip, custom chip implemented on a CPLD that I'm calling Scank for scanner counter, because as you've seen, counting is a big part of what this chip has to do. Horizontally, it has to count to 800 pixel clocks. Vertically, it has to count to 525 pixel lines, as you've seen, and then it has to detect key moments when it has to do something else, like wait or issue the sync pulse and so on. And it also has some shift register logic, and the reason is, just like in the old computers, when you have a black and white computer, each byte from the character definition is loaded in parallel into a shift register, and then that shift register will shift it out bit by bit, dumping it onto the screen. That's how it works. And of course, I will do that according to the standard way of doing that. But there will be another chip, because more than just counting and detecting counter values, You also need the actual video adapter, the character video adapter, or cavia, which means guinea pig in Dutch. So skank is maybe sounds like skunk, and cavia is a guinea pig. So both are little cute mammals. And what cavia will do is, the heavy lifting. It will need to read character tokens or character addresses from the video memory. And based on that, it has to read the corresponding character definition from the character memory. And then it has to load the bytes of the respective definition into Skank's shifter register that I just talked about here. So the whole thing will have 2 chips. Okay, so let's visualize what cavia has to do. Here's the screen. It's basically a 2-dimensional matrix of character tokens. Each of these little tokens here is basically the address of the first byte of the corresponding character in character memory. So it's just the address of this guy here. So if this token here corresponds to an O, then its contents will be the address of the first byte of the O character in character memory. Each one of them will contain the address of the first byte of its corresponding character. So what does cavia need to do? It needs to scan the screen line by line, reading each of the character tokens. I will be using 40 characters by 30 characters. So it has to scan these 40 character tokens here. But once it reaches the end, it can't go back to the next token line. Why? Because by scanning it once, it has printed only the first byte of each character in that line. In other words, if I clean it out again, it has printed only the top of each character, not the remaining 7 lines of that character. Those are not printed yet. So what it has to do, it has to go back to the beginning of the line, to that first address of the line, and do it again, but now index and increment some pointer to tell it that it's now reading the second byte of each respective character. So it will then print the second line here. And it will do that 8 times until it writes the final line of each character in that token line. In other words, until it writes this final byte here. Only then can it wrap around again, and this time go to the second line, where it will write first the first byte, then the second byte, and so on and so forth until the last byte, all the way down until it writes the very last byte of the characters in the last token line. Then it goes back to the beginning and writes the next frame. That's basically what it does. Now, unfortunately, in reality, things are a little bit more complex because you don't get 2-dimensional memories for the screen and 2-dimensional character maps for the characters. What you get is just a sequential list of addresses in memory. So the first few addresses will correspond to the first line, say address 0 to 39. That will be your first token line. The second token line will start from address 40 and it will go all the way to 79, and so on and so forth. So this first each token here will be basically a pointer containing the address of the first byte of the corresponding character, as we've seen. And then you have to read this token 8 times, and each time you have to increment a pointer somewhere, so you can each time index the next byte of the respective character. In other words, you have to make this pass here 8 times, not 3, not 4, but 8 times. On the 8th time, instead of looping back to the beginning, you just go to the next. You just let the counter increment beyond 39 and go to 40. And then you loop back 8 times once you are in 40, between 40 and 79. So you can index not only the first byte, but the second, the third, and the 8th byte of the corresponding character, and so on and so forth. So these are not trivial counters. You need a counter to traverse all the addresses of video memory, but you need to give means for it to know one, how many times it has scanned the line. You need to give it means to know where to fall back. I call it the fallback address. That's the first address of the respective token line, needs to know that too, and it needs to have means to know that in the first pass it's indexing the first byte of the character, in the next pass it's doing the same thing for the second, in the next pass for the third, and so on and so forth. So there is some counting complexity here, but that can all be addressed. I will explain the hardware I'm building in details to you in the next episode. I'm just giving you an overview right now. So this is what Vga does. So now how does the whole thing come together? Here is how it comes together. Here you see on the left the two dual-ported memories. That's the video RAM containing the tokens, and that's the character RAM containing the character definitions. Vga will scan the video RAM, like I just told you, scanning every token line. So it will provide the video memory addresses here. Once the address is put in there, the video memory will reply with the contents of that address, which will be here. And the contents of that address will basically be the first character address corresponding to that character. In other words, the address of the first byte of the corresponding character. And then Vga will take that, and then it will have to index that, adding from 0 to 7 to that address, so it can read out the 8 corresponding bytes of that character here from the character memory where the character definition is. Now, once these bytes are addressed here, they will pop here. So these bytes coming here will be actual bitmaps corresponding to each line of the character. They will be loaded into the shift register of skank, like I alluded before. That's an 8-bit shift register. After they are loaded, the clock of the shift register clock, will clock 8 times, moving the contents to the right, such that each bit of that byte will be presented to the television here in the RGB signal after it passes some analog circuitry. That's very simple, just some voltage dividers and some buffers. So that's how it works. Once all 8 bits are shifted out, then the next byte will come in and be parallel loaded into the shift register, and they will be shifted out again, and the process will continue this way. Now, of course, for each complete byte, for each complete character, there will be 8 bytes that need to be loaded here in this shift register. So this shift register here will work a lot faster than Vga, because for every byte Vga loads into the shift register, there will be 8 clock cycles to shift that byte out. So the Vga clock basically will be 1/8 of the shift register clock. Vga will work at 1/8 the speed, 1/8 the frequency of the shift register. But unfortunately, things are not as simple as I'm portraying them to you. There are some complicating factors. I was giving you a simplified story. So let's go now to what is really going on. What's really going on is this. Remember, this VGA mode I chose has 640 pixels horizontally and 480 vertically. But these old machines will produce screens with 40 times 30 characters. This is a superset, and the ZX81 has 32 times something. This is a superset of the 3 machines I was talking about. Now, if you consider that each character is a little matrix of 8 by 8 bits, then if you multiply both dimensions here by 8, what you get is 320 pixels times 240 pixels. Well, that's a lot smaller. That's 1/4 of the area of what the VGA mode is expecting. So we actually have to double both these numbers here. 240 has to become 480. And 320 has to become 640. So we basically, for every little pixel that the computer sees, the screen has to see a 2x2 version of that. You have to copy that pixel here, the original pixel, we have to copy it twice, once horizontally and then the whole thing vertically. And then we'll be able to fill the VGA screen. Now, how do we do that? How do we do this upsampling, this copying in hardware? Turns out it's very simple, and that's what I'm going to explain to you now, and that will be the end of this episode. Here's what we do. I'll just give you the answer right now, and then I will explain it. What we have to do is to make sure that the Vga clock is actually 1/16 of the pixel clock of 25 megahertz, not 1/8, 1/16. And we have to make sure that the shift register clock here is half of the pixel clock. And then, of course, Vga clock will be still 1/8 of the shift register clock. So why is the shift register clock half of the pixel clock? For the following reason. Every time there is a pixel here, it has been shifted to this point, and then it's presented to the screen, it's printed on the monitor, the pixel clock will tick twice before this bit is shifted out and the next bit is shifted in. And because it will tick twice with the same bit in here, the result will be that this bit will be presented once on the screen and then immediately itself will be presented again horizontally. So we are basically doubling the amount of horizontal information that's presented on the screen simply by halving the shift register clock with respect to the pixel clock. At least that's the theory. That's what I'm thinking right now. I have to see whether this will work. Maybe it will not work. I'm not giving you any guarantees here, but that's my thinking. This whole presentation is about what my thinking is right now. I may change my mind if history is any indication. What I'm telling you now will turn out to be wrong. I'll have to change it. So I'm presenting it to you unedited. This is reality television here. So by doing this, we double the information horizontally. But remember, we have to double it vertically as well. We need a 2x2 matrix, not a 2x1. How do we do that? Remember, we have to traverse a token line here in the video memory 8 times in order to print not only the first byte of the corresponding character, but all of them, all the way to the 8th. So 8 passes of each token line. But you know what? For each of these passes, we have to double the byte. We print the byte and then we print the same byte again. And then the next byte comes and we print the same byte again. And the effect will be what you see here. We will double the information now horizontally. So this will go back and forth 16 times. And the problem we are left with now is how do we index these bytes here? Because here we add 1, from here to here we add 2, then we add 3, but we don't add 16 because that would be here, it would fall outside the character definition. So again, 6 passes per token line, 16 passes per token line. That will require us to use a 4-bit counter that you see here from bits 0 to 3. And then we will have to add something to the address of the first byte of the corresponding character in order to index the other bytes of that character. But what should we add? Should we add all the 4 bits? Of course not, otherwise we would end up adding 16 and we have to add at most 7. Sorry, we would end up adding 15 and we have to add at most 7. The whole thing starts from 0. There is a simple way to solve this. We just ignore the least significant bit when we do this addition, and we just take the other 3. 3 bits will count from 0 to 111, and 111 is 7. And that will have the exact effect we're looking for. So for instance, when this counter is at 0, 0, 0, 0, we will add nothing to this first address here, and we will go straight to the first byte in the character map. So that's when the counter is at 0, 0, 0. Now the counter goes to 0, 0, 0, 1. What will happen? Well, this 1 here is discarded, it's not there. So we will index this thing again, we will print the same byte again, exactly like we wanted. The next count will be 0, 0, 1, 0. Aha, now the 1 is this one here, C1. Now we will add 1, so we will index this byte, just as we wanted. And the next one will be 0, 0, 1, 1. But this one here is ignored. It's this guy here. So we will add 1 again. So we index this guy twice, just like we wanted. And so on and so forth until we will index the last byte twice. And that means that it's 8 times 2, which is 16 passes. So by doing these 2 simple things here, And this small trick here of using a 4-bit counter but ignoring the least significant bit when you index the specific byte, we double the size of the screen and we can fit everything neatly and nicely into the VGA mode I've chosen. That's about it. That's the theory. Again, I'm sure I will become convinced at some point that I've made some mistake in what I'm telling you today, and then I will explain to you what was wrong and what I'm doing to change it, or if I'm giving up on the whole thing. I don't know. But for now, this is it. In the next episode, I will show you in detail the design of Kavya and Skank down to the gate level, and I will share with you all the testing I've done of these two custom chips in isolation. I haven't tested the whole thing together yet, but at this point I already know that they are working in isolation according to my design intent. Maybe my design intent is wrong, but be that as it may, I'll share that with you in the next episode. Alright, thanks for watching, and I will see you then.